Hi, I thought I'd do a video on the Mandelbrot set. I watched a video by Numberphile recently where they sort of went into how the Mandelbrot set is constructed and what defines it. But I felt they didn't really explain it fully. They only showed the iteration across the real axis. They didn't really explain iteration of, a fully complex number. So, and it's not really that hard to comprehend. So I thought I'd do a video on what's going on, how the Mandelbrot set can be constructed, and go into a little bit more detail about how the complex numbers work in this. So on the screen here you can see this is the basic complex number. You have A, which represents the real part of the number, and BI, which represents the imaginary part. And if you watch that Numberphile video, they do a pretty good job of explaining what complex numbers are. And they're essentially just a reference to a point on the complex plane, which, to boil that down, it's just a number which represents a point on a graph. Yeah, simple enough concept. So here's a badly drawn complex plane. So let's talk about the operations we need to do on complex numbers in order to generate a Mandelbrot set. And we need to do three things. We need to be able to square a complex number, basically multiply it by itself. We need to be able to derive the magnitude of that complex number, and also we need to be able to add them together. Yeah, so those are the three operations that we need. So let's first talk about the magnitude of a complex number. So let's take a point on this graph. So this point here, let's do this one. So that point is 1, 2, 3, 4 across and 1, 2 up. Okay, so the real part, is the horizontal, the imaginary is the vertical. It doesn't have to be that way, but that's the way that convention usually does it. So this number would be 4 across, so that's 4 plus, and it's 2 up, so it's 4 plus 2i. Yep. Now, the magnitude of that number. Well, all the magnitude of a complex number is the distance from that point to the origin, to 0. So if I try my best to draw a straight line here, okay, the distance of that line is the magnitude. Now you probably already see that this forms a right-angled triangle and that line is the hypotenuse. So to find this is just basic high school math. It's just a hypotenuse of a right-angled triangle essentially. So it's 4 squared plus 2 squared and then take the square root of that. So 4 squared is 16, 2 squared is 4, 16 plus 4 is 20. So the length of this line is the square root of 20. And that is the magnitude of the complex number. Really simple, yeah? Nothing complicated about that at all. So let's talk about squaring a complex number now. So in order to do this, again, it's a little bit more complicated, but it's still within the realm of high school maths. I did this at school, I'm pretty sure you did as well. So let's take this as an example. So let's say you have x plus y, yeah, and you want to square that. So what you do is you expand it into a polynomial. So you have that expands into x squared plus y squared equals 2xy. Those two are the same. They give the same result no matter what values you plug into x and y. Okay, so now let's do it with a complex number. So here we have our complex number, a plus bi squared. So we expand this in exactly the same way, like that. The only difference is we've got this I there, yeah, because it's part of, the imaginary part. But yeah, it's exactly the same expansion. But if you think about it, what's the definition of I? I squared is equal to minus 1. So here we're squaring bi. So bi squared is basically the same as b squared multiplied by I squared. But I squared is minus 1. So what that is essentially saying, bi squared, is b squared multiplied by minus 1. So what's that going to give you? Well, it's going to give you minus b, obviously. You multiply any number by minus 1, you invert its sign. So instead of plus bi squared, we've now got minus b squared. And that's still a squared plus 2abi. Now something's happened. Can you see that this part is purely real and this part is imaginary? Yeah. So that's the answer. You basically take a, you square it, yeah, and then you take b squared away from that, and that gives you your real part, and then you multiply a by b, then by 2, and that gives you your imaginary part. So to square 4 plus 2i here, we just plug those values in. So 4 squared is 16, and 2 squared is 4, yeah, so that gives us 12. And then plus, and then we work this part out. 4 multiplied by 2 is 8, multiplied by 2 again is 16, and then put the I on the end. And that is the answer to 4 plus 2i squared, 12 plus 16i. And that's how you square a complex number. And finally, let's talk about adding one complex number to another. And that's about the simplest of the lot. It's just simply you add the two terms together. So if we have our original number, 4 plus 2i, sorry about that plus sign being a bit wonky. Now let's say we want to add another complex number to it. So let's say 3 plus 5i. And it's just dead simple, you just add them together. So 4 plus 3 is 7, plus 2 plus 5 is 7i. So 7 plus 7i is the answer to that. So those are all the three methods we need to use to generate a Mandelbrot set. Magnitude, squaring, and adding. And that's it. And they are simple. They're not complicated at all to understand. They're just basic elementary math. So let's talk about the function. So if you take any complex number in the complex plane whose magnitude, remember magnitude here, is less than 2, then we can apply a function to that complex number to see if it lies within or outside of a Mandelbrot set. Now, this function was covered in the Numberphile video, but I'll just go over it briefly. So here it is. The function of z is z squared plus c. Now, z is another complex number that we just pull out of our backside, and we start that number at 0. So that's probably why they call it z, because we use 0 as that number. And c represents the complex number on the plane that you're putting under test. So what you do is you take z, yeah, which is 0, and you square it. Well, that's going to be 0 plus c is going to give you c. Yeah. So you might think, well, why bother starting at 0? You may as well start at c, because the first iteration is always going to give you c. Well, yeah, that's true, but I'm doing it this way because I'm doing it strictly by the definition. And the answer that we get, we assign to z. So what we're effectively saying is we want the new value of z to be the old value of z squared plus c. Yeah. Then once we do that, we take the magnitude of the answer that we get, and we see if that is greater than or less than 2. If it's greater than 2, we say, okay, stop here. That point is outside of the Mandelbrot set. Yeah. So colour it, black or whatever colour you want. But if the magnitude is less than 2, then we do this again. And this time, the function of z is not 0. It's whatever we got last time, squared plus c. Yeah, and again we test the magnitude to see if it's greater than 2 or less than 2. Yeah, and we keep doing that and doing that and doing that until the magnitude of the answer is greater than 2. Now in some cases it will never get greater than 2. Yeah, you could do it forever and it will never get greater than 2. In that case, that point is inside the Mandelbrot set, so you would colour that, say, white. But right on the edges of the set, it gets a little bit strange because there's no defined edge to a Mandelbrot set. And it could take 1,000,000 iterations before the magnitude gets above 2. It could take 1,000,000,000,000. It could take a Graham's number of iterations before this magnitude gets above 2. So what we have to do is we have to have what we call a bailout. We have to say, okay, we've tried it this many times, yeah, and it still isn't greater than 2, so we're just going to call it a day there and say it's inside the set. Even though it might not be, doesn't matter. It's close enough. So we would have an iteration limit. So we would do this iteration, say 100 times, 1,000 times, whatever. And if it still doesn't get greater than 2 by the end of all those iterations, we say, okay, it's inside. And that's how you draw the Mandelbrot set. Okay, so I mean, I haven't really defined this function properly. I'm just trying to simplify it a little bit. But yeah, hopefully you get the meaning of what's going on. So let's go over into Visual Studio now and design an application that can plot a Mandelbrot set on the screen for us. Okay, so here we are in Visual Studio, so let's start a new project. We want a Visual C, Windows Form, C# Visual Forms application. And I'm going to call this mdemo. Doesn't really matter what I call it, does it? Okay, and we'll start that. Okay, so here we go. Let's expand this. So before we get into any sort of graphical thing, let's define complex numbers in here. Now, Visual Studio does have a complex number library, but I don't want to use that because I actually want to show the calculations being done. So I'm just going to define my own class for a complex number. So if we add, sorry, you can't see that, that's off the screen. What I'm basically doing is I'm going to add and then to new item on the other side, which you can't see. And we want a class, and we're going to call this class complex. Okay, so there's the, I'll make it public. This is not you know, a serious application, so don't need to worry about permissions and things. Okay, so the class is simple. We just have a double precision floating point value, which we'll call A, and another one we call B. So that is the real part, and that is the imaginary part. We want to be able to do the functions, the squaring, magnitude, and so forth. So let's do the square first. So we want to square the number. As we said before, to get the real part, we take away b squared from a squared. So that's a squared, take away b squared. Oops. Yep, like that. And we'll assign this a temporary value. Okay. Because, you know, we need to do 2 lines of calculations, and if we destroy one of the variables, it won't be viable. So we can now assign a new value to b. So b is basically 2 multiplied by a multiplied by b. Okay, and then we can assign a to the temporary value before. Okay, so that's just squared the complex number. It's not difficult. Very, very simple. Now the magnitude. Okie dokie. So public. This is going to return a value, so double magnitude of the number, and this is simply going to be the square root of a squared plus b squared. So a times a plus b times b. Okay, and that's the magnitude. And finally, to add. So public void, and we're adding, and this is going to take a parameter of another complex number that we're adding to it. And all we're doing is saying a plus equals ca, and b plus equals cb. And there we go. That's our class for our complex number, and it can deal with all the operations that we need to do: squaring, magnitude, and addition. So let's go back to our form design here, and we're just going to put a picture box in the middle of here. Okay. And we're going to give it a size. Now, will 400 fit? Yep. Okay. So there we go. I'll get rid of the borders as well. So no margin. There we go. We want some code to execute as soon as we run the application. So to do that, we want to assign the event of the form being shown. So we go into the events for the form. Somewhere down here should be shown. That's what we want. Okay, so that event will run when the form appears. So we're going to need an image to put into the form element. So let's define a bitmap. It needs to be the same size as the picture, which is 400 by 400, but let's just make it so that we can change the size of that picture without it, that picture box, without having to mess with the code. So it's going to be picture box 1 dot width, comma, picture box 1 dot height. Oops. Okay. So we've got that bitmap defined now. So now we can start doing the function iteration. So we need to loop through every pixel in that bitmap. So for int x equals 0, x is less than, and that will be the picture box width. X plus plus. And for int y equals 0, y is less than picture box height. Y plus plus. Okay, so that's going to loop through every pixel in that bitmap. But what we need to do is we need to normalize x and y to the complex plane. So essentially 200, 200, the center of the bitmap is going to be the origin 0, 0. We need to convert x and y to a and b. So if we say double a, which will be the real part of the complex number, is equal to, well, it's going to be x minus half of the picture box width, so divided by 2. Yep. Now the whole of that needs to be converted to a double value, so we'll cast that to a double. then we need to divide it by a value that will give us in the range of -2 to +2. The picture box width divided by 4. And that needs to be converted to a double as well. Okay, so that is our normalization calculation for x, and we can just repeat it for b and y just by changing the values. So that's y, and this is the height, okay. So now we have a and b, which are essentially our complex number. So we can create our complex number now. So complex c is equal to new complex, oops, Sam dear, a comma b. I need to put a constructor in here, don't I? Okay, there we go. And we also need the z complex number, which is just 0. So now we need to do the iteration. So I'm just going to put a do while true for now. We'll adjust it later. So we also need a value to count the number of iterations. So int it equals 0. We'll do that. Okay, so let's add 1 to the iterations to start with. So we need to do the function on z. Yeah, so what we do is we say z squared. So let's square z. Yeah, then we need to add c to it. Damn caps lock. Then we need to test if the magnitude of z is greater than 2. So if z.magnitude is greater than 2, then we break, which will exit the loop. And then down here we can say while it is less than, let's do 100 iterations. So what this is going to do, it's going to go through this loop, and it's going to end if the magnitude of the iteration gives us a value greater than 2, or if we've iterated 100 times. When we come out of this loop, our number of iterations is either going to be less than 100 or equal to 100. So if the iterations are 100, that means that we can say that that point is inside the Mandelbrot set, and if it's less than 100, we can say that it's not inside the Mandelbrot set. So we take a bitmap and we can set the pixel of the bitmap x comma y with the color of whatever we've just decided. So it's basically if it is less than 100, if the number of iterations is less than 100, yeah, then it's outside, so we color it black. Otherwise we color it white. Not wheat. White. Okay. And once we've gone through all of the pixels, we can then take picture box 1 and set the image as the bitmap that we've just coloured in. And hopefully, if I've done everything right, that should be it. So let's give it a test. So here we go. Build, and yeah, we've built. So let's start the application. And there we go, a Mandelbrot set. Now usually you would you would define a smaller area for this, just to make the Mandelbrot set bigger. But you know, I was just doing it by strict definition. But yeah, that's it. That's how it works. That's how you define the basic structure. Now this is quite a convoluted way of doing it. It is strictly by definition, but there are much more simpler ways to draw a Mandelbrot set, and of course you've got all the shading and different colours that you can get in there, which you basically do by the number of iterations, how fast it's blowing up or how fast it's not blowing up or whatever. So you would use different kind of calculation here to do that. But this is just the essentials, just showing you how the complex numbers work and how they all, you know, merge together to produce the set. So let's show it again. Beautiful. Okay, thanks for watching and have a nice day.